I would like to extend my gratitude to the creators of the Zoominar, Symplectic Zoominar, because as we are aware of, it started during the lockdown and during the pandemic, and then I was just beginning my PhD, so it was kind of very useful to be in touch with science, even though I was not able to get much, but still it was nice to have something going on. Okay, now I can start with the math. So this was a joint project with Dylan Cant and Egor Shelukhin. And now first we'll introduce the setup of the chord conjecture. So we start with a co-oriented contact manifold, meaning that the corank 1 distribution is given globally by the kernel of a differential 1 form, and this differential 1 form is inducing the volume form via this inequality. And then chord conjecture concerns Legendrian submanifolds of contact manifolds. These are the submanifolds of Y of maximal dimension such that the tangent space at each point belongs to the contact distribution. Then I would like to recall two basic examples, and for the rest of the talk I'll be focused on these two examples. So first one is the standard contact sphere, which is given by the set of unit vectors in the standard symplectic space, and the standard contact distribution, standard contact structure is given by the kernel of the Liouville form on R2n. And then as a prototype example of a Legendrian, we have a standard Legendrian Arnol'd, which is a Legendrian sphere of dimension n-1, given by intersecting the Lagrangian plane P equals to 0 with the contact sphere S to n-1. And the second classical example of contact manifolds is actually, which is something that is related to the theorem that I'll speak about. It's the unit cosphere bundle, which is seen as multiple. There's multiple ways to express it. One way is to set it as set of directions in the cotangent bundle. One can also fix a Riemannian metric and then take the set of unit covectors inside of the cotangent bundle, or take a smooth fiber-wise star-shaped domain and take its boundary. And in these cases, the standard contact structure is given by the kernel of the canonical Liouville 1 form. And Legendrians that we want to consider are the Legendrians which are coming from the conormal Lagrangian. So given a submanifold of our manifold M, conormal Lagrangian is the set of all covectors such that these covectors annihilate the tangent space to n. And these Lagrangians induce Legendrians in the unit cosphere bundle either as their ideal boundary, or one can just take the intersection with the model given by the Riemannian metric or star-shaped domain. Okay, now as for the dynamics, we want to consider the dynamics of a Reeb vector field. So given a contact form alpha on contact manifold Y, Reeb vector field is the unique vector field which is given by the following equations. So the transverse direction is determined by that Reeb vector field should belong to the kernel of the alpha, and then the particular vector from the direction is scaled using the alpha itself. So alpha, when applied to the Reeb vector field, should take value 1. And then in his visionary paper, First Steps in Symplectic Topology, Arnol'd posed the following conjecture, aside from almost all of his conjectures. So given a Legendrian knot in the standard contact sphere, then there exists a non-constant Reeb chords with endpoints on a given Legendrian knot. So let me just give a further example. If we consider the standard contact form on the 3 sphere, then the Reeb flow is periodic, and the conjecture is trivially satisfied because we can just start on any point of the knot, since Reeb flow will close the orbit, and the closed orbit is a particular instance of the non-constant Reeb chord with endpoints on a given knot. But for general knots and general, for more general contact forms and Reeb vector fields which are inducing the standard contact structure, it's actually highly non-trivial to see that such results holds. And this particular question, which was posed by Arnol'd, was solved by Klaus Mohnke, and actually Mohnke proved something more. And here I'll state a more general version of Arnol'd conjecture and what is now known as Arnol'd chord conjecture. So given a closed Legendrian submanifold of a closed contact manifold, then there exists a non-constant Reeb chord on lambda with endpoints on lambda. And this was studied by many people, and later on in the slides I'll present some of the results which are concerning the original question and some of the results which are related to the other work. And another example that I would like to give is that the closeness of the ambient contact manifold is necessary, because we can consider the jet1 space of closed manifold M, which is identified with the cotangent, the contactization of the cotangent bundle. There, the contact form is given by dt, where t is a parameter in R, minus lambda, where lambda is a canonical Liouville form on the cotangent bundle. Then one can check that the Reeb vector field is inducing just the translation in the real direction. So if one takes Legendrian to be the zero section inside of jet1 space, all Reeb chords are starting on the zero section, they are going to infinity, so they never come back. So this condition is necessary. Okay, now as for our theorem, I want to give a motivation which is coming from Riemannian geometry. So given the Riemannian manifold and closed submanifold of M, we can ask a question if there is a geodesic inside M which is orthogonal to the submanifold at the endpoints. And in the case of the round sphere, where we take the equator to be the submanifold, we can obviously see multiple such geodesics. So these geodesics are parts of great circles that are going to the North Pole. And of course, we can also have them from the lower part going to the South Pole, and we can actually concatenate them, and all of them are actually describing all of such geodesics. Although for more general Riemannian metrics, even on the sphere, it's not obvious that we should have such geodesics. And for instance, if we have a complete Riemannian manifold which is not closed, if we take a cylinder and if we take the zero section to be the submanifold, then if we start orthogonally from the zero section, again, we'll have a geodesic which goes to the infinity and never comes back. And this question is solved in the 70s due to Grove, who proved the following statement. So given a complete Riemannian manifold, if n is closed submanifold in M, and if there are no orthogonal geodesics with endpoints on the submanifold, then M should be homotopy equivalent to N. And in particular, in the previous example, we saw the zero section of the cylinder, and there we didn't have any orthogonal geodesics, and cylinder is in fact homotopic to the circle. But as a special corollary, if ambient manifold is closed, then there must be an orthogonal geodesic with endpoints on N, since N and M cannot be homotopy equivalent since they are both closed manifolds. And then how does this relate to the symplectic topology? Maybe I should slow down either, otherwise I will finish my slides too fast. So let's consider the cotangent bundle with the standard symplectic form given by the differential of the canonical Liouville form, which is locally described by pi dqi, where qi are coordinates on the zero section and pi are dual coordinates to the coordinates qi. Then if one takes Hamiltonian to be the kinetic energy, which corresponds to the norm induced by the Riemannian metric on M. Then the flow of this Hamiltonian is a cogeodesic flow, meaning that projections of Hamiltonian orbits are geodesics in the base M. Also, if we take conormal Lagrangian to the Lagrangians to the submanifold of M, which is again set of all covectors in cotangent bundle such that P vanishes along the tangent space to N. This is an exact Lagrangian, and we can actually prove the lemma that there is a one-to-one correspondence between orthogonal geodesics to N and intersections between time one perturbation of the conormal bundle with the conormal bundle, which are away from our submanifold N. Since kinetic energy vanishes along the zero section, it leaves zero section stationary. So we don't want to consider the constant geodesics. We are only interested in non-constant ones. Further comment is also crucial. So in the Grove's result, he used the gradient of the energy functional, and this is not well suited for more general contact forms on the cotangent bundle, which are inducing some different. So if you take some domain which is star-shaped, which is not convex, or which is not even symmetric, so it's not coming from the Finsler metric or from the Riemannian metric, then one could not apply the techniques from the energy functional. There's a question. Well, I'm not completely sure about Finsler case. I'm not sure what should fail.
I mean, it follows from our theorem, of course, but I'd be surprised if we're the first ones who proved it in Finsler case. But anyways,
yes, but I think that Grove is not stating the Finsler case, but I believe that his methods could be adjusted to the Finsler case. It will follow from the theorem that we showed, but I think that his methods are easily adaptable to the Finsler case. Okay. Does this make sense? Okay, I'll continue. Or there is a different correspondence because we want to study Reeb chords. So orthogonal geodesics are in one-to-one correspondence with Reeb chords on the unit cosphere bundle, which is induced by the set of unit covectors with respect to the given Riemannian metric. And we want to consider Reeb chords, which are ending on the lambda n, and lambda n is the conormal lift of a submanifold, meaning that we just take the conormal Lagrangian and intersect it with the unit cosphere bundle. Okay, now we can already state our theorem. So let unit S star m be a unit cosphere bundle, which is an ideal boundary of T star m. So for now, we just want to specify contact structure, not the contact form. And let's take the conormal lift of submanifold of M. Then for any choice of contact form, alpha, which induces the standard contact structure on the cosphere bundle, there is a non-constant Reeb chord in the unit cosphere bundle with endpoints on the conormal Lagrangian. And then according to similar lines of the previous comment that his method, Grove's method, could not be really adapted. It's not only that one cannot apply gradient trajectory to the gradient of the energy functional to deduce homotopy equivalence, but we can also not deduce it directly from the homological argument, because it's not clear from his argument that the geodesic that he's getting is something non-trivial in the homology of the path space.
Okay. Do you assume that N is connected?
Yes, but let me think what would happen otherwise. Well, if it's not connected, we could apply our theorem for every connected component. But it's hard to study the question if we take two submanifolds because it's just wrong. And let me just give one example, if I can add. Add page. So, for instance, if we take flat torus, and if we take, although this union will have an intersection, so we cannot really take N1 union N2, but in this particular case, there is no Reeb chords from a conormal bundle from N1 to conormal bundle of N2, because any geodesic that starts on N2 orthogonally will be parallel to N1, and it can never finish on N1 orthogonally. Although I'm not sure to which extent this answers your question.
Well, to some extent, thank you.
Okay. Okay, let me first talk a little bit about previous results, and then time permitting, I'll go to some details of the proof of our result. So one of the first progresses in direction of the original Arnolds question is due to Cieliebak. And he proved that chord conjecture holds for standard contact sphere where the Legendrian is Legendrian isotopic to the Arnol'd sphere, as in our example of as our first example of contact manifold. And his method was analyzing symplectic homology and how it changes with surgery, concretely with subcritical and critical handle attachment. And then, although I'm not sure what were the dates of the preprints, but Mohnke's result was published before. Mohnke actually resolved the full original question of Arnol'd, and he actually proved something stronger. So if Y alpha is a boundary of compact subcritical Stein manifold, so Stein domain, then any Legendrian in the boundary of the subcritical Stein domain has a Reeb chord. So in particular, since standard S3, standard contact sphere of dimension 3 is a boundary of the ball, which is subcritical Stein domain, we have the chord conjecture in this particular case. And this Mohnke's method was to use the displacement disjunction due to Chekhanov and the construction of a Lagrangian inside of the Stein manifold using the Reeb flow and the Liouville flow. So he constructs a Lagrangian, which is which has topology S1 times lambda. So morally speaking, if this is Liouville direction, this is Reeb direction, he builds a circle using these two flows. And then another important result is due to Hutchings and Taubes, and they resolved completely the Arnol'd chord conjecture in dimension 3. So for any co-oriented 3-contact manifold that is closed, and any Legendrian knot inside of Y, there is a Reeb chord with endpoints on K. And they were using embedded contact homology and Seiberg-Witten theory. And additionally, I would like to mention one quantitative result with respect to the Arnold's question, which is essentially proving that there are genuine chords on Legendrians, meaning that they are not coming from the periodic orbit. So they have the period which is strictly less than the minimal period of Reeb orbit of the given contact form. And these results are due to Zoominar and Cant. Okay, now I'll switch to the cases which are related to our result. So the cases which are proving chord conjecture for the conormal Lagrangians, or the conormal lifts of submanifolds inside of cotangent bundle. So first result, which is actually in two separate papers, due to Abundandolo Figali and separately due to Abundandolo, Portaluri, and Schwarz, is the following. So given pi n, so denote by pi n the space of all paths in M with endpoints on the submanifold n, if the dimension of homology with Z2 coefficients, this was, wait a second. So this part with Z2 coefficients is due to Abundandolo and Figali, or if dimension of the homology with integer coefficients, which is due to Abundandolo, Portaluri, and Schwarz, is infinite, then the chord conjecture holds for a conormal lift of a submanifold. Then there was a result of Ritter, which states that if a map induced by inclusion on the second cohomology is not injective, then Arnold's chord conjecture holds for the conormal lift of the submanifold. And this result uses Reeb-Floer cohomology and the module action of symplectic cohomology on the Reeb-Floer cohomology. And this topological requirement is that to ensure that one can actually find a local system on the cotangent bundle such that it kills the symplectic homology of the cotangent bundle. And this topological condition says that this local system will actually be non-trivial also on the space of paths, so that the module structure, the module map actually can be defined. And since Reeb-Floer cohomology is a module and symplectic cohomology vanishes, Reeb-Floer cohomology also vanishes. And this ensures the existence of Reeb chords. And generically, it also gives a predicted number, lower bound for the number of Reeb chords given by the sum of Betti numbers of the submanifold. And additionally, there is a result due to Will Mary. So under the assumptions that submanifold has dimension less than half of the ambient manifold, or if it is half-dimensional submanifold of the ambient manifold and the ambient manifold has a dimension bigger or equal than 4, then the chord conjecture holds for the conormal lift. And his proof was using a Lagrangian version of the Rabinowitz's Floer homology. And so first theorem might actually give the proof of the general chord conjecture for conormal lifts, although these topological requirements are extremely difficult to check. So it's not known whether the space of paths with endpoints on the submanifold always have infinite dimensional homology with either Z2 or integer coefficients. And as for the other two theorems, one can take, for instance, CPN times the point inside of CPN times the sphere, where the sphere has low enough dimensions so that it covers the assumptions, so that it contradicts the assumptions of the Mary's theorem. And since the map induced by inclusion on second cohomology is isomorphism, then it contradicts the assumptions of the Ritter's theorem. Although in this particular example, it is known that the space of paths has infinite dimensions, but as I said, it's unknown whether there exist examples such that these homologies are finite dimensional. Okay, are there any questions? Okay, if not,
I have a question. I have a question.
Okay.
If I say let P be the space of loops, this free loop space, is it known if the dimension is infinite always, or?
Well, this reduces to the question in algebra. I think it's not known because there is this thing about conjugacy classes, right? And I think actually it's not always known that it's infinite dimensional, neither for the loop space as well.
I see. Whether it's always infinite.
Yes. Because, for instance, there are examples where you could have infinite fundamental group, but finitely many conjugacy classes. It's not known if such an example of manifold could occur.
I see. Okay, thank you. Sorry.
Okay, now let's go into the details of our proof. So in our proof, we are also using Floer cohomology with local systems, but we'll be constructing local systems which are kind of suited for each submanifold. So let us also first recall what are local systems. So given a path-connected topological space and the ring R, local system is a functor from the fundamental groupoid of X to the category of R modules. Or put differently, it's a collection of R modules, Lx, where X runs over the topological space, such that each homotopy class alpha relative the endpoints X and Y induces the isomorphism from the fiber Lx to the fiber Ly, and the map induced by the constant homotopy class is identity, and also the functor is, the functor property is that if you take concatenation of paths and its homotopy class, this should the map associated to concatenation of paths should be the composition of the respective paths. And in particular, each fiber is a module over a group ring of the fundamental group based at the point where we take the fiber. And then we can define what is the homology with local coefficients. So take the universal cover of X and consider the chain complex of the topological of the universal cover. This is a left module over the group ring of the fundamental group, where we have the action by the deck transformations. And then the homology with local coefficients is the homology of the tensor of the chain complex of the universal cover, tensor over the action by the group ring with the fiber of the local system Lx0. Okay, now let's give a little bit of introduction to the Floer cohomology. So if we put a contact form which induces standard contact structure on unit cosphere bundle, then we can identify the set of non-zero covectors with the symplectization of the unit cosphere bundle, and the Liouville form is of the form R times alpha, where alpha was a given contact form and R is a radial coordinate in 0 infinity. Or, for instance, if our unit cosphere bundle is given by the Riemannian metric and it's a set of unit covectors, then R is just equal to the norm of covector P induced by the Riemannian metric G. Then, if we have an exact Lagrangian, which is cylindrical outside of compact set, meaning that it's a Liouville invariant, and then it traces out Legendrian times the ray. And the choice of almost complex structure is of SFT type, meaning that the composition of Liouville form and J gives the differential of radial coordinate. Although here I'm slightly cheating because in the next step, I'll assume that my Hamiltonians are quadratic, because I don't want to go into the details about direct limits right now. So I'll take a quadratic Hamiltonian with respect to the radial direction, and we have the induced vector field as a minus a symplectic dual of the differential. Then the wrapped complex at degree k of our Lagrangian L with respect to the H alpha. And also here, I'm not really specifying how do I extend my H alpha in the interior, but I'll omit these details. So given such a Hamiltonian, then the Floer complex chain complex at degree k is generated by all Hamiltonian chords with endpoints of the Lagrangian, which have Maslov index k. Or if we want to decorate our cohomology with local systems, we will tensor each part with the fiber over the associated chord Lx. And here we consider as our topological space where we consider a local system, it is the space of paths inside of cotangent bundle with endpoints on our Lagrangian. Then the differential will count the solutions of the Floer's equation with boundary conditions on the Lagrangian L. So we have an infinite strip with positive asymptotic x plus and negative asymptotic x minus. And differential is given by the signed count of the rigid elements in the moduli spaces. Or for the definition of the differential for the local system, we can write it in this manner. So it's a sum over all Hamiltonian chords. Then we take the sum over all rigid elements, and each rigid element in the moduli space comes with some sign in front of the generator x minus. And then if we want to decorate this with the local systems, we take an element from the local system, and then we apply differential to x plus tensor with A, so that since each U gives rise to a path between different paths in the path space, we have associated path for the local system, and then this isomorphism gives us where we should map the element A of the local system. And then this is the invariance property of under the change of the contact form. And in reality, I think it's easier to prove this invariance result using the linear Hamiltonians and the direct limit construction. But here I just want to, for the simplicity, I'll state it as is. So given two Hamiltonians, H alpha and H alpha prime, which are quadratic Hamiltonians with respect to the radial function induced by the respective contact forms, then Floer cohomologies with any choice of local systems are isomorphic. So it's independent on the choice of the contact form. And further remark is that actually this is about the extension near the zero section. So we take our Hamiltonian to be quadratic outside of compact set, but then near the zero section we are extending some Morse function on n in a way that the only Hamiltonian chords are actually corresponding to the critical points on the Morse function on the submanifold n, and other generators are actually corresponding to the Reeb chords on the conormal lift. Then from this remark, we can see that we can extract additional data. So we can take the positive wrapped complex, which is a quotient complex essentially generated by the Reeb chords. And then since it is generated by the Reeb chords, we have the following lemma. If there are no Reeb chords on the Legendrian, then positive Floer cohomology will vanish over all choices of local coefficients. And in particular, the full Floer cohomology is going to be isomorphic to the singular homology of the submanifold with pullback local system where I is in the inclusion of the constant paths into the space of paths with endpoints. And one of the crucial ingredients is the isomorphism theorem due to Abodandolo, Portarulli, Schwarz, which was slightly extending to the case for the local coefficients by us. So we have that positive Floer cohomology of the conormal bundle with local systems is isomorphic to the homology of the space of paths relative the space of constant paths with essentially the same choice of local systems, although in reality this local system is on the space of paths inside of cotangent bundle with endpoints on the conormal bundle, and this is the space of paths on the zero section with endpoints on the submanifold, but these two spaces are homotopy equivalent, so we can actually identify these local systems. If there are no questions so far, let's go into the proof. So one of the ingredients is the relative Hurewitz theorem with local coefficients. So given an integer bigger than 1, and if all relative homotopy groups of the pair xa vanish for I smaller or equal than k minus 1, then at the point where pi k is not 0, so pi k of xa is not 0, we have the isomorphism between homology, kth homology of the pair xa with the local system L, and the tensor of the relative kth homotopy group over the group ring of the fundamental group of the subspace, tensored with the fiber of the local system. Okay, now having this in mind, let's give a sketch of the proof of our main theorem about chord conjecture for conormal bundles. From the long exact sequence of vibration, we can actually relate the kth homotopy group of the pair of the space of paths and the space of constant paths with k plus 1 homotopy group of the pair mn. And then since both m and n are closed, we know that there exists some k such that relative pi k should be non-zero. Okay, now let's cover first the simple case, which is already covered in the literature. So let's start with the set of connected components of the space of paths. Well, if there are some non-contractible paths, obviously the positive Floer homology, even with Z2 coefficients at degree 0, will be non-zero, hence we'll have some Reeb chord. Then, if our space of paths is connected, but the relative pi 1 of the space of paths and n is not 0, and then from long exact sequence, we can see that this means that the map induced by inclusion on pi 1 is not surjective. And this map is always injective because, again, from the long exact sequence of the vibration, we have a section from pi n to n by inclusion, and the evaluation at the end point will give us the vibration map. So this map is always injective. So now let's assume the contrary, that we don't have Reeb chords in this case. So this means that our singular homology of the submanifold is isomorphic to the total Floer cohomology in the degree 0. So here we take choice of some local system, and here we take the choice of the pulled back local system. And on the other hand, this is isomorphic to the zeroth homology of the space of paths with endpoints on n. And now let's take the following local system. So over each point gamma in the space of paths, we take the fiber to be the homology, which is the fiber of the universal cover. So let's take the universal cover of the space of paths, and let L gamma be the zeroth homology of the fiber of the universal cover. So this is isomorphic to the group ring over the fundamental group of the space of paths. And since the space of paths is connected, this was our assumption, then the universal cover will be connected as well. Now, recall the definition of the homology with local coefficients. And in particular, we saw that our fiber is isomorphic to the group ring. Hence, the singular the homology of topological space with such a local system will be isomorphic to the homology of the universal cover. And in our particular case, this means since universal cover is connected, at the degree 0, we have that it's just the set of integers, meaning that the homology at degree 0 of submanifold with the pullback of the local system is also integers. But by our choice of local systems, the 0-degree homology will be the group ring over the quotient of pi1 of the space of paths, quotiented by the image of pi1 of the submanifold by inclusion. And according to this conclusion here, this is isomorphic to the set of integers. But then this means that this quotient is trivial, since this is just of rank 1 over z. But in particular, this means that inclusion is surjective, and this is a contradiction with our assumption in this case. And we are left with one additional case where now k is bigger or equal than 2, and now we want to apply the Hurewicz theorem with local systems. So we know that all relative pi I are vanishing for I smaller or equal than k minus 1, and at pi k, for k bigger or equal than 2, relative pi k is non-zero. Now, in this case, we already know that fundamental groups are isomorphic. As I commented, we know that it's injective, and since we pass to high enough homotopy group, we know that it's surjective as well. And since they're isomorphic, we know that each fiber is actually of the local system is isomorphic to the group ring of the fundamental group of the subspace. But now recall the Hurewicz theorem. So Hurewicz theorem for the local systems on the left-hand side takes the quotient over the pi1 of n. But since pi1 of n and the group ring of the pi1 of n is isomorphic to the fiber of the local system, we have that actually this tensor product is just the relative pi k group. So even though we are using just homology, we can recover homotopical data by using this local system. And then, again, using the modification of the Abodandolo-Schwarz isomorphism, we can relate relative homology of the space of paths with local systems with the positive Reeb-Floer cohomology. And since due to relative Hurewicz with local systems, we have identified a relative Kate homology group with the relative pi k of the space of paths, and this was non-zero. This in particular means that we have a Reeb chord. And now one additional remark, which I already pointed out when I was talking about Ritter's work. So usually in the previous results, the methods were by imposing that symplectic cohomology vanishes, the total symplectic cohomology vanishes, and then using the module structure to deduce the Reeb-Floer homology vanishes as well. So even though this is not entirely stated in the work of Mohnke, but the Mohnke's work is also in the case of subcritical Stein manifolds, what is now known that such type of Liouville domains have vanishing symplectic cohomology. So in particular, if Legendrian is fillable, one can deduce a similar result as Mohnke by the similar method of vanishing symplectic cohomology, which means in particular that Reeb-Floer cohomology will be isomorphic to the singular homology of the Lagrangian. In our case, we are not proving the vanishing result of the total Repler cohomology, but we are imposing that in some degree positive Repler cohomology should be non-zero. Okay, are there any questions? If not, let me give some details how to relate the homology of the space of paths with the Repler cohomology. So let's recall the Morse side of the story. So let MG be a closed Riemannian manifold, and let pi n be again space of paths in M with endpoints on the submanifold M. And for each path, for now, let's consider C infinity paths, or we can go to some Sobolev space. So we take the energy of the path to be 1/2 of the integral of norm squared of the derivative of parametrization. And then critical points of energy functional are actually geodesics that are orthogonal to n. And if one imposes the assumption on the Riemannian metric to be generic, actually the energy functional will be genuinely Morse away from the set of constant paths. And then one can set the Kate Morse complex with respect to such energy functional with local systems, with local system L to be direct sum over all critical points of the energy function of Morse index K, and then for each gamma, you just take the fiber of the local system. And then as in finite dimensional Morse theory, although this is a bit more, not a bit more, but much more subtle. So here one needs to find a suitable space to do Morse theory and to prove that gradient flow will have good behavior. But under these assumptions, we can consider the moduli space, which is essentially intersection of the unstable manifold with stable manifold, and we can count negative gradient trajectories up to translation and define the differential with the local systems in the similar fashion as we did in the Floer theory. Since again, because we have gradient trajectories, these are canonically giving us isomorphisms between respective fibers of the local system. Now, this basically, this is a generalization of the finite dimensional case, where we know that singular homology is recovered by Morse homology, and this also holds in this infinite dimensional setting under some conditions on the energy function. Now, let me describe what is the desired space of solutions, which will relate the Morse side and the Floer side. So given a critical point of the energy functional, which is a geodesic, and Hamiltonian chord of the kinetic energy, one defines the moduli space with respect to gamma and x to be the space of all maps from the half-infinite strip to the cotangent bundle, which satisfy Floer's equation. On the S boundary, so if time is equal to 0 or 1, so on the infinite parts of the boundary, we impose Lagrangian boundary conditions to the conormal Lagrangian. And on the zeroth part of our map U, we require that the Q coordinate of our map belongs to the unstable manifold of a critical point of the energy functional. So let me maybe draw another picture. So our solution, so this is zero section. here we have some geodesic. This is one element of the moduli space. And the projection of the zeroth part should belong to the unstable manifold of gamma, where the orange curve is gamma. So this is mimicking Punikin-Salomon-Schwarz isomorphism, although we don't have an obvious connection between the Floer solution and the gradient trajectory, but they are connecting by projection map. And when we started working on this, I remember Dylan and I were discussing why would this even be a Fredholm problem, but in reality, this condition on U is giving a moving Lagrangian boundary condition. And then on top of that, this is parametrized by the unstable manifold of our solution. So if this was a fixed curve, this would have dimension given by the Maslov index of X, but since we are also allowing parametrization by the unstable manifold, the dimension of this manifold will be the sum of Maslov index of X and the Morse index of gamma. Then, when one calculates the energy of a solution in such a moduli space, it's going to be the action difference between the zeroth part of the curve and the action of the Hamiltonian chord. But then, since this zeroth part of the curve is inside of unstable manifold, and using the Legendrian transformation in the relationship between action functional and the energy functional coming from the Legendrian transformation, we actually have that action of the zeroth part of the curve is smaller or equal than the energy of the geodesic gamma. Which means in particular that theta will essentially be identity. So theta map will, in some sense, be a upper triangular matrix, which will have identities or plus, minus identities on the diagonal. Because we can reorder the basis, and we know that, so if Hamiltonian chord X, so we know that XH is giving cogeodesic flow. Which means that each geodesic induces some cogeodesic in a unique fashion, and vice versa. So we can identify these generators, and we can order them by energy or action. And since also stationary solution will be a rigid element of this moduli space, so if we have an S-independent solution, this will just be the Hamiltonian trajectory. And this is why this requirement that this part of the boundary is not lying on the zero section, whether it's living above the zero section. So we are allowing that it actually just coincides with the Hamiltonian trajectory. In the particular case, when gamma corresponds to X gamma, we'll have just one element of the moduli space. And then because of these energy estimates, all other elements from the Floer side that are hit will have smaller action than the energy of our geodesic. And this in particular means that when one arranges coefficients of the matrix theta, which is infinite dimensional matrix, it will have plus minus identity on the diagonal, and it will be other isomorphisms of the local system on the upper side of the triangular. But since we have a triangular matrix which has identities on the diagonal, this in particular means that this induces the isomorphism of respective homologies. And I'll stop here. I finished a bit too fast, but okay. Thanks for the attention.
Great, thank you. Any questions?
I want to return to the question which I had. So imagine this situation when you have, for instance, you have no chords like you wrote curve on a cylinder, right?
Okay.
But now you take two disjoint curves. So then apparently there exists a geodesic, minimal geodesic joining them. And it probably should be orthogonal, right, to both.
Yes.
And so probably this should be just for any two disjoint submanifolds. So
Well, yes.
yeah, so simply.
So in this case, there is actually another argument which is more elementary. You can just take the distance between. So if you take disjoint manifolds N1 and N2. So you can take the Riemannian distance, which is positive, and this will be realized by a geodesic.
So
and
that's exactly what I have in mind, right? But now
yes.
there is this contact version of this result, right? So you have to conormals, right? And the question is whether there exists a chord for every.
Yes. So the
kind of joining this to conormal.
Yes. Okay. Now I understand completely the question, and the answer is yes, because zeroth wrapped Floer homology between two conormal bundles will be non-zero, because it is related to the homology of the space of paths between the two submanifolds, and we obviously have something non-trivially, so which is not coming from the kind of singular homology, because singular homology is zero. Because there is we don't have constant paths, right? We can on the nose take Hamiltonian, which is essentially quadratic everywhere, and however we extend it, it will not have any other generators apart from Reeb chords.
I see.
And then since we
So this was known, or this is kind of what's the status?
I'm not sure if this is written anywhere explicitly, but this follows from Abundandolo, Portarulli, and Schwarz. So for this is even with Z2 coefficients. For this, you don't need any fancy choice of coefficients, not even integers.
I see.
So,
okay. Thank you.
I had a question. I think also the counterexample you gave for the other thing, it maybe is interesting for immersions, because sometimes immersion has a well-defined conormal bundle, right?
Well, but it needs to be of codimension 1, right? So that you can speak about.
I think, yeah, you just wanted to say when you take the like normal spaces at the double intersection points, they're not intersecting upstairs.
Yes.
Yeah. So that I thought, when you have, so the general question, just take two conormals and ask, is there a chord from one to the other? Then in general, I think all you can assume is that they're sort of immersed, the disjoint union of two submanifolds. Yeah. Not the disjoint union, just the union of two submanifolds. Okay, you perturb a bit, maybe. Anyways. But I remember that was sort of puzzling us for a while.
Yeah, but this also solves resolves the question for any two submanifolds which might intersect. I mean, of course, you can think of it as an immersion, but in case that they intersect, it could happen that there is no Reeb chords.
Yeah. Anyways, thank you very much. That was my question.
Can you say something quantitative about like the action of the chord discrete?
No, because we can only deduce things about Maslov index, because our method is just not seeing action at all.
But it seems to be related to the energy of the geodesics that you get, right?
But you see, if that you can say something if your thing is coming from the Riemannian metric, but for the Reeb chords you don't have such a nice description of this PSS type isomorphism. So you can just prove that it's isomorphism, but you cannot say much about the action defects.
Yeah, I guess you'd want to compare it to like the contact volume. What else could you even compare it to? The length, because you can just expand your contact form, so it goes very slowly, the Reeb thing. I don't know if anyone thought about that.
Well, don't give ideas to others.
Just kidding. It's like a systolic inequality. I'm sure somebody, it's like the minimal length of the geodesic versus the contact volume. You could ask minimal length of the chord versus the contact volume. Probably it's sort of maybe trivial. Is these super mini Legendrians?
No, but for instance, you see, like, if the chords is you can increase volume on some other space, on some other part of your contact manifold. Of course, but
yeah, but it's like that. It's like that with geodesics too. You just take your geodesic and I don't know.
Sorry, but for instance, when you discuss interlinking, right? So you have this chord between two Legendrians in certain situations. So this time length of the chord depends on the lower bound on the contact Hamiltonian.
Mm.
So kind of you fix a contact form, you consider contact Hamiltonian, which means kind of ratio, so some bound on the ratio of some other forms to given form. So then you have a bound on the time length, which kind of corresponds to a bound on the ratio of Riemannian metrics, properly scaled, right? So
like a capacity. This is sort of capacity type thing.
I don't know capacity or not, but I mean it's a problem in your method. Kind of, did you try to use some real filtration?
Yeah, we use the filtration to prove the isomorphism, but then we just at the end of the day, it's non-zero.
So maybe you can control this. It seems likely that you should get a bound if you do this more.
Yeah, I did during the talk. I did think of this question of I was looking at this paper of Yaniv recently of chords between two fibers. You could probably ask that for conormal chords. Right? So take your conormal Lagrangian, take your disk bundle, and now out of all Hamiltonian functions maybe compactly supported in the disk bundle, how high can you push them before you create a chord joining the conormal to itself? And of course you have to do maybe like impose that it's non-negative or positive everywhere on the zero section, and then you have this sort of, I guess, interlinking of the zero section with the conormal, right? That's the idea.
Yeah, but in the situation of the path spaces, it's kind of easier to deal with the homology of the path space with ends on 2 points, right? It's known what it is, and there is a lot of points there. And
it does seem interesting. Yeah.
Although, I mean, even though there are local systems, you still have filtration, which is not does not care about local system, right? So there should be something quantitatively.
Yes. Anyways, I should get going though, actually. I have to make it to the university shortly.
Thanks for the comments and questions.
Thank you.
Okay, so thank you, Philip.